Hi, and welcome to the next video in the physics video lesson series on modern physics. Today we'll be discussing the photoelectric effect. The photoelectric effect was discovered by Heinrich Hertz and his lab assistant Philip Leonard around 1887 with work that was being done on cathode ray tubes. The photoelectric effect is fairly simple in its explanation, but the understanding of what was happening and why defied classical wave dynamics, and this is why the photoelectric effect is classified as the second phenomenon to become part of the modern physics repertoire. In brief, this is what is happening. Certain colors of light, when shined onto a certain piece of metal, in this case sodium, eject electrons, which will be known as photoelectrons, which then fly across this open space between the parallel plates, and then a current is measured. In summary, electromagnetic radiation can push electrons free from the surface of a solid, and this process is called the photoelectric effect. A material that can exhibit the photoelectric effect is said to be photoemissive, and the electrons ejected by the photoelectric effect are called photoelectrons. Electromagnetic radiation, light coming out of this flashlight, depending on the color and the frequency really, hit the metal and cause electrons to jump out. They're called photoelectrons because the light waves hit the electrons and they push them out of the metal, and then they are attracted to the positive end of this plate where they then complete the circuit and create a current. It's not until Einstein gets involved in this project that we realized we have a quantization of light. And so we start to view light not as a wave, but now as a photon particle colliding with these electrons. I'm going to get into this explanation in some detail in just a moment. Here I have a simulation showing a photo source shining red light onto a piece of potassium plate, and we can see that these red squiggle lines represent photons of light or bursts of wave energy. Now I have this set with a very low frequency, which is a low energy, so you can see that as the light strikes the surface, no electrons are being ejected from the surface. But I'm going to turn that up in a moment. I've now turned the wavelength down to 700 nanometers, and I've changed the shade of the light slightly. So I've increased the frequency, but you can see that this increased frequency is still too low to release the electrons from the surface of this metal. So I'm going to adjust the wavelength again. I'm going to shorten the wavelength, increase the frequency, and thereby increase the energy, and let's see what happens. So now I've decreased the wavelength to 610 nanometers, and I've increased the frequency, and you could see that this yellow light is not causing ejection of electrons from the potassium plate. Even though it's a higher frequency, it's still not energetic enough to do any energy transfer and release. I've now turned down the wavelength to 580 nanometers, and you can see green light is striking the potassium plate, but there still is not enough energy to buy an electron or to remove it from the potassium metal itself. So here we are at 540 nanometers, and we're at some varied shade of green. And I'm going to adjust this wavelength slightly, and you're going to see a difference. Now I've decreased the wavelength, and I'm down to 520 nanometers, and for the first time you can see that each wave that strikes this metal ejects these photoelectrons. But you could see that these photoelectrons do not have enough energy to escape completely, and they do not make it across to the other side, so no electrons are detected. But if I begin to increase the energy just slightly, you'll notice two things. One, the photoelectron makes it all the way across to the other side and it gets counted. And two, the speed of these exiting electrons is faster than the ones from a lower impact energy from the last example. I'm going to turn this up slightly. Now we're in the blue zone, and you can see that these photons, or these energy packets, are hitting the potassium, and when they do, here's 3, 4, 5. Look at the speed at which the ejected electrons travel across this space between the parallel plates. Let us look again at an even higher frequency. We're going to leave the blue zone and start getting into the violet zone, which is much more energetic. Look how quickly the photoelectrons zoom to the other side. So as soon as there's impact, they ricochet electrons right out of the surface. This is the photoelectric effect. Light only at a certain minimum frequency known as the threshold frequency, that's really the energy it takes to break an electron free from the outer shell of the atom of potassium or whatever metal you're dealing with. Anything above that frequency, you buy the electron with the energy that it costs to break it free, and whatever's left over is your kinetic energy the electron has during its flight ejection. Let's turn up this frequency some more by reducing the wavelength, and we're going to get from violet, we're going to head towards ultraviolet. And you can see how quickly these photoelectrons eject and travel across the distance between the parallel plates. High frequency is high energy, and the kinetic energy of the photoelectrons is higher. Here's an example of a wavelength of 180 nanometers, which is a very high frequency. And we are out of the visible range. That's why the wavelengths here are drawn as black, because you can't see them with your eye. Let's go down to 100 nanometers. Look how rapidly the photoelectron ejects from the surface of the metal. So to summarize, this piece of metal has a certain binding energy which holds its electrons in its outer shell. When you attack this piece of metal with the light carries with it a certain amount of energy. And it can basically buy an electron out of the shell. It purchases, it spends the energy to remove it, equal to the binding energy, and whatever's left over, that is the kinetic energy that it has. So let's use simple monetary terms. If it costs $1 and you attack it, or you approach it with $100, then you spend $1 to buy it, and 99 of the dollars are its kinetic energy. It's that simple. So to summarize, that the photoelectric effect will not occur when the frequency of the incident light is less than the threshold frequency. Different metals have different threshold frequencies, and most elements have a threshold frequency in the ultraviolet region of the electromagnetic spectrum. So we have potassium, beryllium, titanium here in this example, and here are the spectral charts of light that can affect emission. What this chart shows you very clearly is the frequencies. Red has the lowest frequency and the longest wavelength, and violet has the highest frequency and the shortest wavelength, and then beyond that you have ultraviolet and other energies beyond that. These energies can buy, particularly for potassium, an electron when the light is somewhere between green to violet. So if I shine green light on a potassium plate like I did in the simulation, the electrons will pop off, but they will move very slowly. But if I shine a frequency of dark green or light blue, you will still get ejection from the potassium surface, but they will have more kinetic energy. And then of course, if I shine the violet almost at the edge of ultraviolet, you will see very fast emission off the surface. There are two conclusions to the photoelectric effect. The first conclusions, which were incorrect, I have here in red. The experimental findings did not agree with wave theory. It was believed that with increasing intensity or brightness, you should have increasing wave height and therefore energy. And with increasing frequency, you would have an increased number of electrons. But that is not what happened. And this was what was very troubling because, as I said at the beginning of this video, this is the second experiment that defied wave theory. So eventually Einstein arrives on the scene and he applies the energy quanta that was used by Max Planck in his black-body radiation, and he realizes that the increasing intensity of the light, which is its brightness, increases the number of ejected electrons. It's a one-to-one effect. Instead of treating light like a wave, we now treat it like paintballs. and each paintball of a certain color has a certain energy. One photon paintball hits the metal and one electron jumps out. And as you increase the frequency, meaning you go from red to orange to yellow to green to blue to violet, you increase the energy of the color of the paintball or the photon. The ejection of the photoelectron depends on the frequency of the photon, the paintball, that strikes it. And as I said earlier, you have to buy this electron off of the surface. It costs energy to remove an electron from the surface of the metal. But once you've purchased that electron, whatever excess energy you have, that is what goes into the kinetic energy of the ejected electron when it flies across the screen as it did in this sample right here. That is kinetic energy, which is simply the incident energy minus something called the work function. So Einstein's revelation was that the energy of the ejected photoelectron is equal to the energy of the incident light minus the energy of the work function, or the cost to buy an electron from the surface of the metal. Little historical note: Albert Einstein won his Nobel Prize in Physics for explaining this process and providing the mathematical background, which you can see right here. He discovers that the kinetic energy is equal to the energy of incoming light minus the energy required to buy the electron from the metal. We know that photon energy is equal to hf, and then of course, since v equals f lambda and v is the speed of light, we can now have a relationship between energy and wavelength. They are inversely related, and the work function itself turns out to be a value of energy equal to hf0, and this 0 means the minimum frequency required for releasing the electron. And there you have it. This concludes our lesson on the photoelectric effect. Thank you for watching, and I'll see you in the next video.